Okay, so now we really go to communications and try to understand the how one communicates in a quantum world. But first, we discussed that you can always diagonalize a matrix, a density matrix, but generally, which means that you can find a basis of vectors, of orthonormal vectors, where this matrix is diagonal. Let's say that I call it phi. Okay, so let's say that my rho A is a sum over k of some pk's, and it's diagonal in some representation of phi k's. But I just take some other orthonormal set of vectors, psi i's, and in this basis, my matrix won't be diagonal, but still I can, because this is a mixed state, then I have probabilities of having these different states, and to this probability distribution, I can identify the entropy. So let's define Q of I. This is the probability of having a state of i's, which I can write as a, I need to take my rho A and project it on psi I and psi I. That would be my Qi's, but my rho is, as we said, is a sum over k of pk phi k, right? Well, phi, let me write it in a bit more detail. So it's pk phi k phi k psi I, right? So what I will get a set of matrix element between I and k. We call it. Generally, it's again this overlap projection between two different states. So I may say that this is equal to this probability distribution is a sum over k pk dik squared. Yeah, this is the same matrix element here and here. So now we met a stochastic matrix when we considered Google random walk, which means that the sum over all over any column was equal to unity. But for ik is double stochastic. Namely, if I sum over any I, dik is the same as sum of any k, dik, and it's equal to unity, which means that if you take any k, it's definitely projected somewhere. So if you sum all the projection over all i's, that will be unity. And the same here. It's called double stochastic matrix. Now I may ask, this is a probability distribution, right? So what I may take q log q and compute its entropy S of q. What would we expect? We knew that if I make it diagonal, for diagonal, my classical Shannon entropy is equal to the von Neumann entropy. Now I'm making I'm taking states, my basis, such so that my matrix is generally non-diagonal. I still can compute the probability of such states, but what I expect is that the entropy would be larger than von Neumann entropy or smaller. What's your intuition? Not clear. There is more uncertainty about such when I have a diagonal representation, namely that my states are clearly in terms of this my matrix, I have different states, each one with own probability. Or I can have a very on top of it an off-diagonal element, which means that I do not exactly distinguish the state. So see how it works. So if I take this S of Q, what I need to do, I need to take this pk, right? And yeah, actually, I would rather call it probably, would call it square root of d. And this would be, so dik is psi I phi k modulus squared. So that would be like this. It will be just simple notation. So this will be OK. So now what I would have pk dik logarithm pk plus logarithm dik. Right? That's my entropy of this distribution. Right? This is my distribution, and sum over chi and a. So if I sum it over I, this would give me unity. So the first term, sum of this over I, it's unity, which means that this is just S of P of my Shannon entropy in the diagonal representation, which is von Neumann entropy. But then I have something which is over here. And again, what I would have here is the sum of pk dik logarithm dik. And this is, you can write it as a yeah, I would rather maybe write it, it's better like this. So it's pk dik. I would probably the best write it like this. Minus S of P. OK, yeah, this will be probably. So what I did, well, I need to compute this, but I wrote it as divided it here, and this is P log P sum over K. So minus and minus give me plus. So I would write it as S of P plus D of Q and P. And it's always larger than S of P. So this is just a, there is more uncertainty if you are working in the off-diagonal representation. Now, what I want to discuss is communications. So if I'm communicating, but letters of my alphabet are quantum states. So somebody take this, low temperature DORs or whatever and bring it from place to place, or using some fiber optics, and we would like to ask, what would be the rate of communicating this information if I'm working with the diagonal states? Apparently, there is no choice. My von Neumann entropy is the same as my Shannon entropy. And in a sense, I just using this diagonal states as letters. And my uncertainty is determined by this distribution. So any letter that I obtain would give me an information which is on average rate would be the entropy S of P. But there is a more non-trivial situation. What if I'm using a non-orthogonal? If I'm using non-orthogonal states, as for example, we used here, right? These are non-orthogonal states. So I have these states, and this it can have a non-zero projection one into another, and I might try to use both of them. And then it's clear that my matrix won't be diagonal. in this kind of representation, whereas it contains non-orthogonal elements. So it's clear that its entropy generally will be larger than this. So what would be then the rate of transfer of information? This is the question that I want to ask. So for example, I'm really using non-orthogonal states, and the probabilities of this state define distribution which has entropy larger than the von Neumann entropy, because it's only in the when I diagonalize the matrix and compute Shannon entropy, that would be my von Neumann entropy. So the question that I now pose is, what would be the real information transfer rate, right? And as usual, I don't like proving much theorem, so I'll give you an example, and it will be clear which one is. What's your intuition? Which one? Larger quantity or smaller quantity? Which would be the real rate of information transfer? Smaller quantity. Unfortunately, life is always like this. It's always smaller quantity. So let's take a particular example. So let's say, again, I take in all my examples will be qubit. So I take a state which is 0, but a second state, I would call it S. It would be 1 over square root of 2, 0 plus 1. Right? Is that what I did? Yeah. So now, you see, I'm using two possible states. Just my system is prepared this way. They are non-orthogonal. There is projection. Well, this is S state, right? There is one and there is another. And so now I have a probability distribution. Let's say this have probability P of B. My system has probability P to be in this state, a probability 1 minus P to be in this state, right? So this is, and of course there is entropy associated to this thing, which is P log minus P log P plus 1 minus P log 1 minus P. This is just an entropy of qubit associated with this distribution. For you late, what we are now doing, we are trying to send information by non-orthogonal states. So the question is that if I write my matrix, my density matrix, in the representation of non-orthogonal states, it's non-diagonal. And what we established that its entropy is generally larger than its entropy in a state where it's diagonal, because it's state where it's diagonal, it is a Shannon entropy which is equal to the von Neumann entropy. So now, when I'll be sending and sending and sending, what now I'm doing, I'm repeating this typical sequences shtick, which we did when we considered classical information, just using states instead of letters. So what we would have, we would send these quantum states, and we would have, after n steps, we would have the state 0, like a tensorial product, np times, right? And we would have a state which is S, which is n1 minus p times, right? So this would be what would be our sequences. And now, of course, if we will do in measurements, we'll be sometimes obtaining out of S 0, sometimes 1. But when n is very large, then zeros and 1 would appear with equal probability in S, which means that what essentially we will get here, 0 half time and 1 half time, right? So that would be what we would get if we would just look at it. So now it essentially tells us that we would have zeros with a probability n1 minus p over 2 and unity with a probability n1 minus p over 2, right? So that was what will be kind of our typical sequences, okay? And so now, if we ask what is how many ways to choose this n1 plus p over 2, it's a totally different entropy, right? That would be now need to say that I need to take s of 1 plus p over 2, let's denote like this, which would be 1 plus p over 2 log 1 plus p over 2 minus 1 minus p over 2 log 1 minus p over 2. And I need to compare it with p log p plus minus 1 minus p log 1 minus p. Okay? So essentially, I'm saying that if I'm sending this letter and just naively saying that the probability is p at 1 minus p, it will be this rate of information. But if I recode it into zeros, ones, right, then I would be having this rate of information. There's two different rates, right? Just well, depending on the of p. So what I'm asking is essentially what is larger, this or this? Well, it depends on p, right? And you remember, by the way, how this S of p looks like? It's between 0 and 1. Somebody remembers how the entropy of a qubit in which we send one part as a p. Anyway, this is a Bernoulli distribution, it's called. Like, well, when p goes to 0, it's 0, right? When p goes to unity, it's 0, and it's symmetric. And when p is equal to 1/2, trust me, it's 1/2 log 2, 1/2 log 2. So this is something which is like this. Okay, good. Now this is yet another thing which is just this one shifted, etc. Anyway, you can find out that this is equal to z when p is equal 1/3. It's a nice arithmetic exercise, but it tells you then when p is larger than 1/3, this is better. Well, because when p is less than 1/3, you need to encode it differently. Okay, I'm not doing this arithmetics, but well, you can check it yourself. It's essentially because you see on one part it's just a monotonic curve. So what it tells me? It tells me that if I would look at this state, they are non-orthogonal, look at their distribution, it would suggest that I would have this rate, but I essentially can recode it in different language. And looking at, again, the rate of information is essentially how fast with n increases the number of typical sequences. And so when I wrote you a typical sequence in terms of this 0 and 1, and it would give me a smaller rate than this one if p is larger than 1/3. So it's essentially the confirmation that if you're working with a non-orthogonal state, there is less distinguishability between them. So you would think that your rate of transferring information is this one, but it's not. And now I want to give you a particular example just to see how it works. So let's say this one, let's take p 1/2. When we know that it's guaranteed, right, that when p is 1/2, then we know that S of p is unity. Let's now compute S of rho. So what essentially I suggest, and it's a nice, simple, but very useful exercise, is to take we take two non-orthogonal states, this and this, with equal probability. The entropy of this probability has its 1 bit. Let's now compute the von Neumann entropy of a density matrix. Because density matrix now, if we would just write it in terms of zeros and ones, then what will be rho. So again, with equal probability comes this and this, right? But you see that zeros are coming more often than unities. How many times more often? Like this is 1/2, this is 1/2. So my zeros come 1/2 plus 1/4, because it's 1/2 of this. So what I would find out that my zeros comes with 3/4 and my units come with 1/4. And again, that 0 and 1 comes also with a 1/4. So this is the density matrix for this state. I may observe 0, this is 0, 1, 0, 1, right? And it's non-diagonal because it's a non-orthogonal state, but we may now diagonalize it. So what we need to do, we need to find eigenvalues of this matrix, eigenvectors of it, and then we, after we find this eigenvalues, it's enough, we can compute the von Neumann entropy, which would be a Shannon entropy of these eigenvalues. So what you would essentially get is that you would get 3/4 minus lambda times 1/4 minus lambda equal to 1/16, right? That's an equation on eigenvalues. And so you can obtain lambdas. It's a quadratic equation, so you get lambda squares plus 3/4 plus 1/4 plus lambda minus 1/16 equal to 0. That's your quadratic equation for eigenvalues. So you get lambda 2 plus minus square root of 2 over 2, right? Yeah. So that's your lambdas, and now you can compute a respective von Neumann entropy in this case, which would be lambda 1, 2. So that will be lambda 1 log lambda 1 minus lambda 2 log lambda 2. And you can see that this is just 1 plus 1 over square root of 2 log minus 1 over square root of 2 log 2 plus square root of 2 over 2. So if you take this 2 and this 1 and this 2 and this 1, log 2 is unity. Log 2 is unity. They come with the same sign. So you get 2, right? And then you get this and this with different signs, and this with the same sign. When you get with the same sign, you would get minus 1 log 2 plus square root of 2, 2 minus square root of 2. This is, of course, 2. So you get another 1. And you get also their ratio, which would be minus 1 over square root of 2 log 2 plus square root of 2, 2 minus square root of 2. That's what you get out of it. OK. So this would be, yeah, 1/2. This is approximately 3.4, right? This 1.4, 3.4. This is approximately 0.6, so this is about 5.5. If you take a logarithm, it will be 2 plus something. So you can, all this compute, you get approximately 0.6 bit. This is von Neumann entropy. This is S of rho. Again, as we said, when it's non-diagonal, then it is less than in any, when it's non-diagonal, it's more than the true, but the rate of information transfer is the most efficient encoding, and this is given by this S of rho, and this is a particular example. Okay, and the last thing that we really need to consider about it is that if we use now the letters which are not we assume that these are pure states. So our density matrix were created out of pure states, just a sum of tensorial combinations of it. But what if our alphabet is made of mixed states? Like this. Let me consider this case. So what now I'm saying is that my rho is the sum of pk, rho k, but those are by themselves have a non-trivial entropy. They are some mixed state. Okay, and now what I want to compute in this case is what would be S of such rho. So it will be sum over k, pk rho k, logarithm of pk rho k. So when I'm doing this, what I take logarithm of pk, right? So I have sum of trace. Somehow I forgot a trace. Okay. So now what I would have here is a trace. Trace in terms of a matrix. The matrix here is only row. P's are numbers, just scalar positive numbers. So I would have trace rho k, pk log pk. I take log of the first part, sum minus, and I would have a second one, trace sum over k, pk rho k, logarithm rho k. And that would be something which would be trace of rho is unity. Every density matrix has a trace of unity. So this is just S of p. This is S of p, my just a usual distribution. And what I would have is I would have again, p is a number, so I'm taking trace of this. So trace of rho k log rho k is sk, is a entropy of every such mixed state, von Neumann entropy. So it would be a sum of pk sk. So again, what I would just have shown is that if I have a density matrix built out of a mixed state themselves, then its von Neumann entropy is larger than its Shannon entropy. The Shannon entropy is just an entropy of a probabilities of this state, of these numbers. That's my Shannon entropy, right? But now von Neumann entropy somehow mixes this uncertainty about which state with the uncertainty of any given state, right? You see, so this is now something which is in this particular case. So, and of course, the rate of information transfer that I get out of here, again, is given by the smallest number, because what is inside this state I cannot convey anyway. So every time I am obtaining something, I resolve this uncertainty. So this is the information that I obtain. Okay. So if now I want to wrap this up, and I give you kind of a simple table. So information transfer rate. So if I'm working with orthogonal pure, let me write it, orthonormal pure states, and they are also diagonal, my S of P equal to S of rho, and this is what it is. Okay. Now, if I'm working with non-orthogonal pure states, it was this example, right? They were non-orthogonal, but still they were pure states. There is no uncertainty here, right? This is a superposition, but superposition is a state. So in this case, what I find out that S rho is less than S of P, but it is the guy. So here they are both, and here it is this one. Okay, and in the third case, where it is mixed states, in this case, S of rho is larger than S of P. So a part of the probability of having a state, I have also extra. So von Neumann overcounts. Well, it counts a real uncertainty, but when you transfer information, you cannot. This is your letters, right? So if your letters are blurred, right, it's still a letter. You just treat it as a letter. And in this case, again, it is the smallest quantity out of it. It's somewhat non-trivial, and now a punchline here you would not believe. So what if I have non-orthogonal mixed states? Again, so if I would have both troubles here and here, what would be the rate of information transfer by such states? You wouldn't believe it. Nobody knows. Namely, that there is no general proof in this case, but people still believe that if you look at, if you take the quantity which is S of rho minus sum of pk sk. Okay, you can. They are now non-orthogonal, which means that you need to write it as a sum of a sum of a pk sk, but your rho is a sum, so it is a sum of a pk sk minus sum of a pk rho k sk. Does it remind you something? So what I'm saying is that here it was S of p in this case. So here we consider it a case where we have a mixed state, but they were orthogonal. We made out of them diagonal matrix, and we found this. So if I take S of rho and subtract the sum of entropies of mixed state, I'll get my Shannon. Generally, when I have mixed state but also non-orthogonal, this difference, which you can write like this, because your rho is a sum. This is not S of p. It's quantity which is called Holeva information, and it is believed that it is the true rate. It's like mutual information, right? So it's an entropy of A plus B plus C, whatever, minus sum of entropies, right? But so far, nobody was able to prove in any general case that this is the true rate of quantum information transfer. So we're really working in a very kind of present-day field, okay? And this is on a more general things about quantum information transfer. I don't want to tell you. This is again, I mean, Preskel at Caltech gives 3 semesters on this subject course. So this is a big field. I don't give you much proofs. I give you some computations. But what I really want to spend the rest of this lecture is to show you teleportation. Well, first of all, it's Nobel Prize is given for this, which is kind of a very timely subject. But it's also somehow clearly illustrates this to how actually this bizarre nature of quantum information. Okay, so now what I want to discuss how one can really move around quantum states without anything moving around, if you wish. And this is something which is related to the possibility of purification. So again, a density matrix, as we say, where is my density matrix? Whatever. Any density matrix is a Hermitian matrix with a trace 1. It describes a system A, and it's purifiable in the sense that I can always imagine a system B which makes A and B together in a pure state. There is no classical analog to it. Classical analog of density matrix is a probability distribution, and it cannot be purified in any way, right? So this is a very strange thing, and most of its strangeness could be related in the conditional entropy. Well, it's actually, well, anyway, let's formally, I just first want to remind you what was the conditional entropy in the classical case. So if I defined S of rho A, B, conditional of rho B, right? I can say that this is S of rho A, B minus S of rho B. Exactly like I did it in classics. Let me write classics over here so that if I say S of A, oh, well, there we call it differently. In a sense, the conditional entropy tells me that what else you need to know except B to establish A, right? Or you can take S of B minus S of B under A, and that was your mutual information between A and B, and it was always positive. Now look here. A and B, in what we consider, is a pure state. But entropy of B then is the same as the entropy of A, and it's positive, non-zero. Which means that my of course, it's not conditioned on everything. It's just kind of a formal kind of combination. But still, it tells me that it's actually negative. So when my conditional entropy is positive, as in classical things, it tells me how many bits I need to add to completely specify it, right? What means negative quantity, okay? So now my whole system is in a definite quantum state. My subsystem, A, is in a mixed state. It has a non-zero entropy. The remainder, B, has exactly the same entropy. What it tells me, is it any meaning or just has no meaning? And that what, out of thinking of such things, people understood that as in a classical case, positive conditional entropy measures how many bits you need to specify the system. In a quantum case, the negative conditional entropy actually measures how many teleportations you can make. And I did not define what is teleportation, but now really that was kind of a teaser, and now I want to tell you what it's actually about. So now it will be communications. Maybe my A will be Alice and B will be Bob, and they will be trying to communicate. So A has a state, and she wants to teleport the state. But she cannot have any quantum channel. Namely, what she can send classical information. Classical information means that there would be some just numbers, letters, whatever, but not quantum states. But what she can do is that she can have with Bob something shared. So as we discussed, if she would try, how I would call it probably, I would call it A naught. So she has A naught state. She does not know what it is, because you cannot know what is your state. This is really something which is very important to understand. So you cannot know what quantum state you have. The moment you know, the state is no more, right? Still, you want not destroying it to let somebody have it. Namely, create the state which is exactly like your state. Well, generally it's impossible, but it's possible using this property which we return over and over, which is called entanglement. So you can now exploit the fact that you can have between A and B, between Alice and Bob, you can have something which they share. And using this shared resource, they can now use this trick. So let's imagine, so let's assume that everything is a qubit, right? I will be very, very simple. So I assume that in between A and B, there is A1 and B1, and it's a qubit pair. And they share it, and it is in the entangled state. Namely, that this, whatever this would be value of A, and this would value of B. But what they have, that psi A1, B1 will be 1 over square root of 2, 0, 0, plus 1, 1. Like in this example, but in a maximally shared state, A equal to B, right? When the entropy P equal 1/2, entropy is maximal. So this would be my state of this pair. And what then happens is that they separated. This Bob took his B1 part and went somewhere very far away in another galaxy. Okay? So now B1 is here, and A1 is here as a state. And now, but they are entangled, right? So even though they are far away, somehow we assume, and again, this is something which essentially all the technical difficulties actually creep in, that you really want to have an entangled pair far from each other, which means that you need to really take them away without all the noise in the world breaking their correlation. Okay? That's your A1 and B1. Now, what Alice wants, she wants to do some joint measurements on these two things, but she does not want to destroy A0, which means that this must be a measurement which tells her nothing about A0. Because what is important is that the moment you learn something about it, that means that you learn whether it's in a state of 0 or 1. That's it. It's already, so what I call it, yeah. So it means that it needs to project. Again, there will be a double qubit. One will be for A0, another will be for A1. But she needs to take it in such a state of two-qubit system, so that any measurement would not let you distinguish in what state A you are. And there are 4 such states. So let me list all of them. Let me just. So the states are, of course, of the same type. So it's 1 over square root of 2, 0, 0 plus my 1, 1. And again, I am talking about A0, A1 system. Or similarly, I can take 0, 0 plus minus, or 0, 1 plus 1, 0, 1 over square root of 2 in the space of A0, A1. So what it tells me that if all my measurements will be projection of such a state. So if I know that my double qubit system is in such state, I don't know which state is A0. Right? It could be in 0, it could be in 1 with equal probability. Which means because it's equal probability, and generally it's not equal probability, it's something, well, which means that I learned nothing out of such projection. Okay? So now, imagine that, now let's talk what is this state. So we assume that this A0 was some kind of a general superposition, as we say. So it was alpha 0 plus beta 1. So it was kind of a general superposition with alpha and beta having their own, well, their sum of modulus squared is unity, but generally they can be whatever it wants. And now what I really want to see what happens when I did this measurement. And this measurement brought something like, I don't know, this state. So what I'm saying is that I took my initial qubit A0, attached to it A1, they are now joint system, made a measurement, and they give me this result. Okay? Every measurement gives you some definite state. One measurement gave you this result. Now it does not tell you anything about the state of A0. It's just kind of coordinated the state of A1 to the state of A0, what they did. Okay? Now, if you may look at it from the viewpoint of the extended state A0, A1, B1. Because the moment that you did here something and your A1 is entangled in B1 and you did this measurement, then you know what is possible, what are the possible combinations of this triple. Let's see what is possible. So it now has 3 positions, right? So again, my A naught could be alpha 0, but the moment that I have alpha 0, what I can have? I can have 0, 0 plus alpha 0, 1, 1. That's my 2 possibilities. Plus, I can have beta, and then on the first position there will be 1. If the first position is 1, then I may have either this or this. So I may have 0, 0 plus beta 1, 1, 1. Okay? That's all my all possible state. Now that I learned that I projected and my result of projection gives this, it tells me that this is impossible, and this must be me the sign minus. So this is what I know. They were all possible combinations of it, and this is the result of measurement. It gave me this one, right? And this tell me that what would be about B1? B1 will be in a combination alpha, this is B1, alpha naught minus beta 1. No matter what was the state of B1 before, the moment I did this measurement with this pair A naught A1, and it gave me this answer, my B1 immediately started depending on A naught, which is alpha A beta, right? Tons of paper written whether this is a communication faster than light and all this were written. Of course, at this point, there is no communication. Communication needed when Alice will send something to Bob, which would be, call it by phone or any classical. But what essentially she wants him to recreate. Again, nobody knows alpha and beta at this point, right? We just know that B1 is in this state. Just know. Because those are possible states of a triple A naught, A1, B1. The measurement ruled out these 2 things. So looking at the third position here, we find out that B1 now in this state. What you need to do to recreate A naught, which is the same with a minus, you need to multiply it by a matrix which is 1, 0, 1, minus 1. So Alice, looking at the result of her measurement and seeing that it's now coming this and this with a sign minus, sends Bob a classical message: take your system and flip the sign by this, flip the sign of projection on 1. This is a standard. You just multiply it by this matrix. Okay? So you see, at this moment, what was conveyed from A to B is a classical information. What they had before, of course, was this entangled pair, which is A1, B1. Without this entangled pair, there would be nothing happened. And, but the result of it was teleportation. And the people really did it in the lab. So you can really take an entangled pair of atoms, spin or photons, and making something on one of them instantaneously change no matter how far is B1. It's truly bizarre. I really want you to feel how bizarre it is, right? And this is, of course, we're choosing the maximally entangled state. And this is a maximally entangled state, and this is a maximally entangled pairs. So which just to magnify the effect. But generally, qualitatively is for any degree of entanglement. Okay? Is that clear here? Or at least you have any feeling for it? Okay. So what we did, we say that if there is entanglement between two states, then separating them, we can take this quantum system in a given state together with another system, do type of measurements which do not distinguish between states of a first system, and depending on the result of the measurement, we immediately change this B1, but we know how we need to change it further to make it equal to A0. Okay? So in a sense, we kind of sacrifice A1, but we get, so what it has to do with the conditional entropy of which we exactly talk here. So if you look at it, let's say over here. So first of all, if we have what is the S of rho B in this case? So what we had A1 and B1. You remember where is my here is A1 and B1 is a pure state which is maximally entangled. So if I look only at B, what would be its entropy? It will be unity because the probabilities here is 1/2 on both sides, and the whole state was pure. So as rho A, the rho B, this is as entropy is equal to unity, okay, and also it is the same as S of rho A0, right? And now if we look at S of rho A not A1 and B1, because this is a pure state, then this is just S of rho A0, and it's equal to unity. Now, if we compute S of rho AB over rho B, which is S of rho A0 A1 B1 minus S of rho B1. This is 0 because this is unity and this is unity. And this is a necessary condition of this teleportation, so that if I have such a situation, and for such situation I really need this to be perfectly entangled, right? Then I can make teleportation. So if my this relative entropy is negative, and it's possible to be negative, this could be also a pure state, and this is still. It tells me how many acts of teleportation I can make. Because eventually, when it's 0, I can make my last act of teleportation. Because when I do teleportation, each time I would be raising it by unity, just sending one bit, one quantum bit. So in a sense, it shows some kind of a bizarre antisymmetry or or symmetry. So if your conditional entropy, classical, is positive, it tells you how many bits you need to send more to specify A under a given B. If your conditional quantum conditional entropy is negative, it tells you how many acts of teleportation you can make to reproduce on B that many states of A, which means that you, every time you have a shared qubit, you can send 1 bit of information. Every time you have n shared bits, your conditional entropy will be minus n bits, and you can make step by step each time lowering this number. So more or less, I'll probably won't go into this more into this quantum communications. Of course, it's a very booming and an interesting science. It's still not clear how practical it is. But what was, I think, interesting by some kind of ricochet, and that's what we discussed in the last lecture, is what it tells us about physics. So the next lecture will be this viewpoint from the quantum information theory, from the viewpoint of entanglement entropy, on physical object like black holes, or just any physical object, from the viewpoint how much entropy or information it can contain. And also what I shall do in the last lecture, I'll give you a very brief encoding of the course. So I'll try to tell you all the course like in half an hour, which means that I believe that it's really important exercise. When I was an undergrad, I had a friend who was actually a musician. But he wanted to learn some physics, but did not spend much effort. So usually before, and we had, that was cruel times, you would not believe it, we had oral exams, which is kind of 5-6 hours of grilling. And but he somehow managed always on the lowest grade. And because the evening before exam, he asked me to tell him what it's all about, like in 2 or 3 hours. And it was usually, and that's how I learned to tell what it's all about without much details. And of course, it was a lot of bullshitting in it. So, I mean, sometimes you really kind of, you start blurring things that you lie at some point. But kind of it's useful, okay? So what will be also the last lecture, it will be trying to code all the information in the course to its most basic element, like in this information bottleneck. So I want to be as compact as possible, still have some usual information with what was truly in the course. Okay. So if you know some people who were in the previous lectures, I very much kind of recommend to come. And it will be not next week, which is Thanksgiving, but December 2. As it will be last lecture. Okay. Good. Thank you very much. And see you in 2 weeks.